Hello everyone, welcome to the second lecture, module number 1. So hope you're all staying safe and healthy. Please do continue to do so. And without further ado, let me just share my screen and turn on the video. All right, so this is going to be lecture 2, module 1, as I just mentioned. And the agenda for this particular module is going to be to see how to get inverse Laplace transforms and also to categorize the system according to the different types of poles. So the system responses categorized according to the different types of poles. But before that, here's one point which I had actually discussed in the interactive session the previous day. That is, an improper transfer function will always correspond to an acausal system. And I hope that I wasn't sure that the recording was right there. So I just wanted to put it out here. So you see, when you have an improper transfer function, if you actually expand it by partial fractions, what you would have is generally the sum of a polynomial and a rational function. And that polynomial will eventually lead to derivatives. And whenever you are taking derivatives, remember, you cannot find the derivative of a signal by just knowing the instantaneous value of the signal itself. You need some other value at some other point in time, especially in the future, right? Because you're trying to find out what is the direction towards which the signal is headed. Therefore, you're looking into the future, which violates the tenets of causality, and therefore it will be an acausal system, a system which involves such derivatives. All right. So I wanted to get that out of the way. Now, before we actually launch into these two, I just want to first, again, give you a very concrete motivation behind this. So let's take an example of a differential equation, right? And show you how this Laplace transform actually helps us. And this will also highlight another point, which is about why when we define Laplace transform, we are taking the lower limit of the integration as 0 minus rather than 0 plus. That is why we so hung up on that particular point. So this will illustrate both at one go. So here's the example of the system that I'm considering. This is the differential equation. All right. Well, let's say the input is the delta, the Dirac delta. All right. So t is greater than 0 minus. That is where we are seeking the solution of the system. And x 0 minus is given as 1. Okay, so one of you asked me, like, when we are taking the Laplace, when we are taking the transfer function, why are we saying that the initial conditions are 0? As I clarified then also, so for the practical purposes, it really matters not if you're considering the initial condition to be 0, because the Laplace transform is a very powerful tool. And especially when you have such non-zero initial conditions, you'll see that how the Laplace transform helps you in solving this differential equation at one go without having to plug in or substitute values. It's just that the transfer function is defined in a way which always assumes that the initial conditions are 0. Yeah, because the transfer function is concerned with the response of a system to some applied input rather than the initial conditions. That's why you zero out the initial conditions when defining the transfer function. Okay, nothing more to that point basically. Okay, so now let's take the classical method of solving this differential equation. Okay, so what would you do? Now suppose you're trying to solve for t greater than 0 plus, right? Because you know that the impulse exists for a brief period in time. Let's say here 0 minus and 0 plus, right? So this is 0 minus, this is 0 plus. So beyond 0 plus, basically this becomes 0. So then you can consider the differential equation for 0 plus, for t greater than 0 plus to be given by this is equal to 0. Which of course you know how to solve this particular equation, right? You know that this equation's solution is given by x of t is equal to x of 0 plus e to the power minus 2t. Right? The question is, in a physical or a practical system, no one's going to give you what this t0 plus is, right? What the value of this function at 0 plus is. What you will always be given is this particular value. So then this turns out to be useless. The point I'm making is that if you're trying to solve this by classical method, just by blindly following the differential equation and trying to solve it this way, will not aid you in getting the response of the system to this impulse input. So you have to make some arguments, additional arguments. Yeah. What is that argument going to be in this case? if you look at this particular differential equation here, since the left hand side must equal the right hand side at every instant, all right, the argument I'm making is that therefore, because the right hand side has a discontinuity, yeah, has this impulse, yeah, the right hand side has this impulse, the left hand side must also have that impulse, right? But then x cannot have that impulse, x cannot be equal to that impulse, right? So the only way that this can happen is if x dot is equal to the impulse, or in other words, x has a discontinuity at t is equal to 0. Yeah. So listen to this argument very carefully. The argument is that the left hand side and the right hand side must equal in this expression. And if that were so, then there must be an impulse here sitting somewhere here, right? If this fellow had the impulse, then this fellow would have the doublet. But clearly there is no doublet here. So the only way that the impulse can come here is if this fellow had the impulse, right? If this fellow has an impulse, then you integrate the impulse and you immediately see that x will have a discontinuity at t is equal to 0. And therefore, x of t, sorry, therefore, x of 0 plus minus x of 0 minus will be equal to that discontinuity. What is the discontinuity? It is the integration of the delta function. It is nothing but the integration of the delta function from 0 minus to 0 plus delta t dt, that is just equal to unity. So then this is how you obtain this, right? Do you see the point here? The point is that merely knowing this t0 x value at 0 minus doesn't suffice. You have to find the value of 0 x at 0 plus through this argument. And now that you know that x0 plus is equal to 2, now you can solve this and you can say that this is nothing but 2e to the power minus 2t. So herein ends the classical method, the solution by the classical method. Okay. So we are, I mean, you can clearly see, right? Every time you encounter some system like this, you have to make these arguments. We are not very comfortable doing these all the time. You have to be very careful in making these arguments and equating the left and right hand side and all that. What if we could get rid of this all at one go? So suppose in the Laplace transform definition that we had considered earlier, suppose you had given this as 0 plus to infinity ft e to the power minus st dt. Suppose you had considered 0 plus instead of 0 minus. Would that have been a problem? In fact, there is a name for this. It's actually called the L plus transformation. Okay. The point is this going to be of any use to us in solving this differential equation? Okay, let's see. So what we had was the original differential equation. I'll rewrite that again. X dot, I'm dropping the t plus 2x. Yeah. So we have x dot plus 2x is equal to delta t, right? Now, if you're integrating both sides, if you're taking the Laplace transform from 0 plus, remember that beyond 0 plus, this fellow has no contribution. So you again land up with the same situation as before. What you will now have is this minus x of 0 plus, remember, because now you're integrating from 0 plus 2xs is equal to 0. Yeah, so it appears like it's good. So let me call this x0 plus, yeah, because there's a plus Laplace transform. So what happens is then you have this x plus of s given by x plus of 0 plus, sorry, this is basically not x plus, no? This is just the time domain. So why am I writing it this way? There's no need for this. Sorry about that. Yeah, that was an error. Yeah. So what we have then is and you can take the inverse Laplace of this to obtain the solution as before. All right. The point is now the point is that this still does not solve the fundamental problem. Who is going to tell you what this x0 plus is? Again, you have to resort to the same sort of argument that we had used here and do this. So it's basically useless then. If you're considering from 0 plus, this sort of a Laplace transform does not help you. Now consider that we are going by our definition of Laplace transform, the way we have defined it, which is ft e to the power minus st dt, right? Consider the same equation. Now you have xss, I'm just straight away taking the Laplace transform, and you have x0 minus, all right, plus 2xs, yeah, is equal to 1. Why? Because now that we have considered the lower limit of the integration from 0 minus, this integration of this delta, the convolution, or rather the Laplace transform of this delta can be written as 1. And this makes all the difference. How so? So now we can write xs as 1 over s plus t plus x0 minus over s plus 2, which is nothing but, now you use the value that x0 minus is 1, so you straight away get 2 over s plus 2, which is nothing but 2 e to the power minus 2t. All right. So I've already used the fact that the Laplace inverse of 1 over s plus 2 is e to the power minus 2t. Okay. We'll see that shortly. Hopefully you've already revised this as we did this session on the last Thursday. Right. So the point is that by using this, you don't need to use any of those arguments. Yeah. The process becomes much simpler. Okay. So I hope that you see the merit of using this definition of Laplace transform. This is particularly important when you have a discontinuity in your response at 0, or you have some impulses in the input. Right. So this can tackle even those cases. Right. So that is why we prefer to go for this. Okay. And of course, the definition of initial value theorem, as we have described it in the previous lecture, now you'll begin to see the merit in that. Okay, the other point that I wanted to clarify, sort of, in this lecture is as follows. So, remember that we had defined this output yt is equal to, in general, okay, if you're not imposing any causality or the initial relaxation of the system and stuff like that, then this is what it's going to be like. Okay. Now, suppose your input is e to the power alpha t, where alpha is a complex number. All right. Suppose this is your input to the system. All right. Then what happens? Then we can write yt is equal to integration from minus infinity to infinity. You have h tau, and you have e to the power yeah minus alpha tau into e to the power alpha t d tau. Now clearly this term we can pull it outside the integration, so we can write this as e to the power alpha t integration minus infinity to infinity h tau e to the power minus alpha tau d tau. All right. Now this is basically the both-sided Laplace transform. Okay. So let me call this e to the power alpha t, and just to distinguish it from the conventional Laplace transform, I'm putting this hat notation. Of course, instead of s, please note this is infinity. Huh? This is infinity and this is alpha. The two are not the same. Okay. It's infinity and that's alpha. So just to distinguish, now your argument instead of s is alpha. All right. So the point is that if you are applying, an exponential input where the number alpha is a complex number, then your response to that exponential input is going to be just that exponential input multiplied by this complex variable. You agree that this is complex variable, right? Because this is a function, it's a rational function typically of a complex number. So it's a complex variable that has a magnitude. So this has two parts. It has h hat of alpha, which you can call as m, and it has phi given by the angle. Yeah, it's up in the polar coordinates. That's how you represent a complex number, right? You can write a complex number like this, the magnitude m and the phase of phi, right? So basically what happens is, to an exponential input, like so, the output is given by this gain. It's basically, this is the gain, and it has two parts. One is the pure scaling, the other is the phase. So basically when you give an input exponential, two things happen to that. One is it gets scaled up or down, and then it gets rotated by some phase, either a phase lead or a phase lag. Okay, we'll talk more about these when we later cover Bode plots, and you'll see that this alpha, when it's purely imaginary, it's basically tantamount to applying some sinusoids or cosinusoids, that sort of a response. All right, so this is the point I wanted to make. The other thing is, if you now assume causality, what assumption of causality, what it means is, now you are applying this e to the power this exponential signal throughout every instant of time. But remember, this is the impulse response. So what about the impulse response? We know that for a causal system, ht is equal to 0 for t less than 0, because the impulse is applied at t is equal to 0, right? So this is t minus 0. So the impulse is applied at t is equal to 0. So before you apply the impulse, there cannot be any response due to it if it is causal. So for causality, we have this. Now if you impose the causality on this, what you get is yt is nothing but our conventional. Yeah, so from 0 minus, the impulse starts to appear. So therefore the impulse response can also not exist before 0 minus. Yeah, so then this becomes e to the power minus alpha t and e to the power alpha t. Sorry, this is going to be tau. Yeah, so this is tau d tau, and then we get back the regular Laplace transform, right? I'm getting rid of the hat now. So this is what we have defined as our Laplace transform. So to an exponential input such as this, where alpha is a complex variable, complex number, this is actually alpha. Yeah, because this is alpha. So the Laplace transform, instead of the s variable, you're now using alpha, right? So this is an interesting and important insight. You apply exponentials, this is the way you get it. So in order to get a transfer function, you don't really need to carry out this integration. Yeah. So let me give you the detailed example here. The same example that we had considered earlier. Okay, for that particular system. So let's say you have x dot plus 2x is equal to a delta. All right. So let's say you are considering, no, sorry, not delta. Now you're going to apply some exponential signal as an input to it, right? So that's what we're going to do. All right. So this is going to now be e to the power alpha t. All right. This is our input. Now, if you want to let x t is equal to h of alpha e to the power alpha t. So you know that this is the applied input. So you can guess, as from the previous result, that this is going to be the form of the output. Now you plug this in here. All right. So what is x dot? It is nothing but alpha h alpha. Yeah. This is alpha h alpha e to the power alpha t plus 2 h alpha e to the power alpha t is equal to e to the power alpha t. All right. Now if you want to solve for this, you will easily see that h of alpha is nothing but 1 over alpha plus 2. So therefore h of s, you've got your transfer function, is equal to 1 over s plus 2. So remember that this is how it helps us. So if you want to find out the transfer function of a system, you substitute the input to be an exponential, and then you plug it in here. Yeah, it's always easier to do that. You plug it in here, and this is how you get the transfer function. You can bypass this. So for a given differential equation, you can bypass this process of carrying out this sort of an integration. Yeah, and this is actually makes life a lot easier. Yeah. Now, if you want to find out this impulse response in the reverse method, right? Now, from the transfer function to the impulse response, you can easily see that ht is equal to Laplace inverse of hs is equal to e to the power minus 2t. So, having seen all of this, you now understand that knowing how to find out the inverse Laplace transform of a given function in S domain is very important, because at every step I have kind of ignored that as trivial step, but it's not really trivial. The reason why I have ignored it as a trivial step is because the nature of the function is very simple, and this is straight away out of the Laplace transform table. You can read it off that it is the exponential, right? So you know that when you have you have this particular result, right? That if you have say f of s is given by integration 0 minus to infinity f of t e to the power minus st dt. This is the first step, and this is equal to the Laplace transform of ft. All right. Then let's say you have f bar of s is equal to minus 0 minus to infinity, and you have e to the power at ft e to the power minus st dt. Yeah. Now I'll leave it to you. There's only a simple substitution at some stage, and you'll be able to immediately see that this is nothing but equal to f of s minus a, thereby leading us to conclude that the Laplace transform of e to the power minus, e to the power, let it be plus, no problem. It really doesn't matter, because the sign will change on either side. Okay. So if you have e to the power at ft, that's given by f of s minus a. Yeah, if it was minus a, then it would have been plus a. So basically now you know that for a step input, for a step signal, it is 1 by s. So when that s is shifted by minus 2, then it basically becomes an exponential. Yeah, and we are just assuming that the step is there. So if you want to be very precise about this, you can also multiply it by the step. Right? Right. So we know that this result holds. Yeah. So it turns out that there are certain pieces in the puzzle that help us to know exactly how to obtain the Laplace inverse. There is another important, crucial, important result. So remember, this is an exercise. Fill in the steps in between. It's not really that difficult. Just a little bit of playing around with the integration, the change of variables. If you change the variables suitably, you'll be able to do this. Nothing much really is there to it. Yeah. Now let us consider the integration ik is equal to 0 minus to infinity t to the power k. T to the power k e to the power minus st dt. All right, if you do this, the first step comes out to be this integration by parts, e to the power minus st over minus s, and t changes from 0 minus to t tending to infinity minus integration 0 minus to infinity, then you have k t to the power k minus 1, because you're differentiating this, e to the power minus st dt over minus s, right? So all the while k is basically a positive integer, all right? So this, again, you can check that this particular term, when t tends to infinity, because of this, it goes to 0. When t is equal to 0, then due to this, it goes to 0. So this vanishes either way. This doesn't exist. So all that you'll be left with is some k over s, this k that you've chosen, this particular k over s, I k minus 1. It's a recursive relationship. Now for the special case I0, you already know that it is 1 by s. Yeah. So using this relationship, you can get that I1 is equal to 1 by s square, I2 is equal to 2 by s cube, so on and so forth. So in general, we'll be able to infer that Ik is equal to factorial k over s to the power k plus 1. Yeah. So this is another important result that people use very often. This is handy in, so this is the first thing, the shift. Second thing is this multiplication by t and its powers. Yeah. So this gives you an idea of the kind of form in which we want to get our S domain functions. All right, because that will enable us to quickly infer what the inverse Laplace transform will be, rather than every time perform that integration in the S domain as is defined as the inverse Laplace transform definition, right? Okay. So having known of these things, basically what you'll be dealing with are rational functions. So you'll be given some g of s is equal to some numerator polynomial whose roots are basically the zeros of the system, and some denominator which will look like this. So there will be, this means product, by the way, product of terms. This is basically I is equal to 1 through k, and these will be s minus ei to the power, okay, what should I call it? To the power rpi. Okay, this is the form. So I've drawn a very longish line. You don't need that. Okay. Yeah. So let me just shorten this because we don't need that line to be that long. Yeah. So this is going to be the typical form of a transfer function where pi are distinct complex numbers in general. Yeah. When you have a polynomial, yeah, in this form, this is exactly how it's going to be. So you have k distinct complex numbers here. PIR, basically there are k distinct complex numbers, but each of them, so basically so there are k of them and each of them can be repeated, right? So RPI is the number of times they're repeated. So if RPI is 1 for every PI, then it's basically k distinct complex numbers and only appearing once. So basically the degree of this polynomial is then going to be just k. But if they are repeated, right, then the degree of, so degree is going to be degree of this, let's call this polynomial in the denominator as ds. So degree of this is going to be nothing but summation RPI, I from 1 through k. I hope that you see this, right? It's pretty straightforward to see. Now the point is, having been inspired by these results, it turns out that if you can write this GS in the following form, which is k, okay, this is I is equal to 1 through k, I is equal to 1 through k, and then you have another term, which is a double summation. So this is going to be RPI, let's say, what should I call it? Di is equal to 1 through RPI. So this is going to be, let's say, AI, comma, PI upon S minus EI to the power DI. All right. So this is our desirable form. Why is this a desirable form? Because this is exactly where we want this to be. So we've got this old fellow, this GS, to look exactly the way we want it to. Why? Because once we have it in this form, straight away we can read off. We don't even need to memorize anything. We can read off what the inverse Laplace transform will be for each individual term, right? And because of the linearity of the Laplace and the inverse Laplace operations, if we know the Laplace inverses of these individual blocks, we can take the sum of those Laplace inverses, and that will be the Laplace inverse of the sum. Yeah, sum of the Laplace inverses is equal to Laplace inverse of the sum due to linearity. So therefore, if we can express this in this form where these, if we are allowing for the PIs to be complex, then we can say that these AI PIs, they also should be allowed to be complex. Okay. So if we get it in this form, then we know that each individual term like this, so when you have it d raised to the power di, for instance, you know that it was going to involve some term like t to the power di minus 1. And when it's shifted by this p in the frequency domain, you know that there will be e to the power pit. Yeah, with some, you know, ai, pi, and possibly some di, the factorial di. Yeah. So that is how these terms will each individually be gotten into this form. Of course, there is still some work to be done. For example, if this is going to be a complex number, then this is also going to be a complex number. So you don't want your responses, because remember, we are typically going to deal with polynomials whose coefficients are going to be real. That's how your transfer functions are going to look like. And if you leave it at this, the job is not complete. So we'll see gradually what I mean by that. So there will still be some work left to be done. So I think the best way to go about it, instead of keeping it in this notational form, is to take some examples. All right. So I'll take some examples, and hopefully with those examples you'll be able to see how we plan to go about this procedure. All right. Okay. So let me first take the example such as given by okay, g of s is equal to, so I have taken certain things for granted here, which need not always be a thing that you should do. You should actually try to verify that it is indeed, whatever I'm saying here is legitimate. Okay. So suppose you have gs given by s square plus 3s plus 2. All right. So I can factorize this as s over s plus 1 into s plus 2. All right. So I can factorize this as s plus 1 into s plus 2. You can check that this is indeed the factorization. Straightforward. Now, this we plan to write as sum k1 over s plus 1 plus k2 over s plus 2. The question is, what guarantees that this is exactly, I mean, you can always get uniquely these k1 and k2. The guarantee is that, of course, if you cross multiply, so if you have s over s plus 1 into s plus 2, and if you write this as k1 over s plus 1 plus k2 over s plus 2, if you cross multiply this, you will have s is equal to k1 times s plus 2 plus k2 times s plus 1. Yeah. So you will basically be left with equating the coefficients on either side. So you will basically have k1 plus k2 is equal to 1, and 2k1 plus k2 is equal to 0. Yeah, you'll be solving two linearly independent equations in two variables, which you should be able to easily do. And eventually, you will come up with a solution that k1 is equal to minus 1, k2 is equal to 2. The point is, as you might easily guess, this is a quadratic factor. It yielded just two of these, right? As the degree of this polynomial increases, you will have more and more coefficients. You'll have more and more terms to the right. And then, if you want to equate every coefficient, see, all of these are coupled equations. What do I mean by that? So when you're given an equation of the form ax is equal to b, when a and b are matrix, a is a matrix, a square matrix, let's say a full rank, yeah, then you can find the solution for this system, right? But wouldn't it be nicer if you had a structure in A? For example, if A is like a triangular matrix, an upper triangular matrix, let's say, or let's say A is basically a diagonal matrix. Then it's much easier, right? In this case, you can just keep back substituting. First solve for the last one, then back substitute it and obtain the next one, and so on and so forth. In this case, you don't even need to do that. You can straight away read off the solutions. So clearly, when we are solving linear equations in this form, we desire certain special structures which help us in quickly solving this, without inverting the matrix A, right? So by the same token, faced with this problem of solving these coefficients, we want to make our task simpler. So how do we do that? It is very easy here. Why? Because look, this holds for all S, right? So what if you choose two specially chosen S's such that these equations become decoupled? So let's say you choose S is equal to -1 and S is equal to -2. Since this is going to hold true, this is identically true for every S, you can definitely equate it with these two particular S's. What is the benefit? When you choose S is equal to -1, this term vanishes, so you are just left with this, right? So that is how you get this. Yeah? Excuse me. Right. And when you choose the other one, you solve for K2. So you can solve for K2 by putting S is equal to -2. All right. And you can solve for K1 by putting S is equal to -1. Yeah, by freeing up the terms. All right. So now, following in the same principle, now we face a new sort of a problem. Yeah. So remember that there's no restriction as to which method you use. If you feel that you want to solve for this coefficient by directly cross multiplying, there's nothing stopping you. You can always do that. There's no right or wrong in this method. It's just that life becomes a lot simpler if you had taken this transfer function GS. So to summarize, if you had just taken S plus 1 times GS and let the limit S tending to -1, yeah, then you would have obtained your K1, right? You would have obtained your K1, and by the same token, if you had taken S tending to -2, S plus 2, GS is equal to K2. Yeah. So you can do this, or again, as I said, I repeat, you can always equate the coefficients and get back to the fundamentals. Yeah. Question is, when you have something of a different form. So for example, let me see what example I have noted down here. Okay. So let's take another, as we are used to doing this, let's take another differential equation itself. Okay. So let's say the differential equation is x dot plus 2x x double dot plus 2x dot plus x is equal to 0, where x at 0 minus is equal to b. Sorry, x dot at 0 minus is equal to b, and x at 0 minus is going to be a. All right, you want to solve this differential equation. So again, if we take the Laplace transform, I leave it to you as an exercise. You can see that there's going to be x squared s minus s x 0 minus x dot 0 plus 2sxs, sorry, minus 2x0 plus x of s is equal to 0. So from which you can easily then write, you please fill in the steps, take this as an exercise and practice problem, okay? Plus 2a plus b upon s plus, okay, upon s plus 1 whole square. All right. Now, how do you go about this? Yeah, that is an important question. My claim is that you can always write this xs as this form: a1 over s plus 1 plus a2 over s plus 1 squared. Please check as part of an exercise. Please check as part of an exercise that this is indeed doable. What do you have to do in order to check that this is indeed doable? Yeah, see, look at this x. So that's why you're dealing with strictly proper transfer functions here, right? So basically the degree of the numerator is 1 less than that of the denominator. That is what enables you to basically write it in this form. All right. So check that. Again, if you want to find out what A1 and A2 are, you can straight away just equate coefficients. Yeah, but equating coefficients, as we've seen, involves solving equations that are coupled. So if you take this form, then you will have AS plus 2A plus B is going to be equal to A2 plus A1 into S plus 1. So in this case, of course, it's pretty simple, right? You can immediately get that A2 is equal to A plus, no, sorry, it's not, it's actually coupled. So I shouldn't be jumping steps. I shouldn't be jumping steps. See, that's the mistake. So yeah, so what we can write is A2 plus A1 is going to be equal to the constant term, that is 2A plus B, and A1 is going to be A. So this is still better because you can do this because this is like a triangular system, right? So you can plug this in here and you can get that A1 is equal to A, and A2, obviously if you substitute here, is going to be A plus B. All right. So you get your system in this form as x of s is equal to a by s plus 1 plus a plus b by s plus 1 squared. And now you clearly know what these are going to be like. So you can get your entire system solution, differential equation solution. Yeah. You can get your solution as a e to the power minus t plus a plus b is going to be a t e to the power minus t. Yeah, this is your solution. All right. The point is that all this seems very well and good. Yeah, but note that what is the equivalent shortcut here? Like here you have this shortcut, right? You could use these limits like these to evaluate K1 and K2. The question is there a shortcut for getting the same for this big A, this A1 and A2 here? See, you can immediately notice that nothing prevents you from taking this x of s is of the form a1 by s plus 1 plus a2 by s plus 1 whole squared. So if you again multiply this by s plus 1 whole squared xs, limit s tending to minus 1, what you will then be left with is the a1 will vanish. So this is a1 times s plus 1 limit s tending to minus 1 plus a2. So this term vanishes, right? So basically a2 can still be obtained in the same spirit as before, but you are stuck when you arrive at this a1. So what is the way out for this? The way out is, of course, if you multiply just by a single s plus 1, that doesn't solve because both of them will vanish. Yeah, rather one of these will have an s plus 1 below, so the limit will not exist. Sorry, not both will vanish. This will still remain a1, but the a2 will have an s plus 1 in the denominator, so you cannot apply this limit. So multiplying by just one s plus 1 does not solve the problem. So what do you do then? What you generally do in such cases is you differentiate. All right. So how do you differentiate this? You solve for this a1 using the first method, right? And then you multiply this, cross multiply this. So the method, if I were to outline it, would be as follows. You take this a1 over s plus 1 to s plus 1 squared plus a2 into s plus 1 squared into s plus 1 squared, right? This is going to be your, what was the numerator polynomial here? As plus 2a plus b. This is going to be yeah, this is going to be as plus 2a plus b. All right. So this clearly turns out to be A2 plus A1 into S plus 1. Now if you differentiate both sides with respect to S, what you will then have straight away is A1 is equal to A, right? Exactly the same thing that we had here by equating coefficients. So this differentiation method works. You can look up in the textbooks, they have these factorials and different, and it looks very complicated, but as you've seen now, it's really not that complicated. The idea is whenever you have a pole of degree, a pole that's repeated, let's say di times, like in this expression here, just cross multiply by s minus pi to the power di. Okay, so by cross multiplying by s minus pi to the power di and applying the limit s tends to pi, you'll be able to solve for one of the coefficients. For the remaining coefficients, you just keep differentiating successively. So you differentiate once, you'll get the coefficient for 1 over s minus pi to the power di minus 1. If you differentiate twice, you'll get the coefficient for 1 over s minus pi to the power di minus 2, so on and so forth. Yeah, so I don't want to give you those formulas. You can look up, of course, but at least we'll leave you with this spirit that this is doable and this is very simple. Yeah, it's not really that difficult. The formula might appear more complicated, but in reality, the actual thing is not that difficult. Okay. Now what happens is we leave you with the last part of this, which is when we have complex poles. Okay. So when you have complex poles, of course, as you might have guessed by now, we have already covered this within our paradigm here. The moment we allow this pi to be complex, right? So it turns out that you can use the same method. Only thing you need to be careful now is that there will be a real part of A1 and an imaginary part of A1 and a real part of A2 and an imaginary part of A2. Yeah. So for example, let's say you have something like this. You have 5s plus 2 upon s plus a whole squared plus b squared, where a and b are positive integers. Okay, could be anything. Let's say a and b are positive integers. I'm sorry, positive real numbers. Actually, any real number would do, but anyway. So now if you write this as, let's say, a plus ja bar, where upon s plus a plus jb plus b plus jb bar upon s plus a minus jb. All right. If you write it in this manner, where a bar, b bar are real numbers. Yeah, this is following the same spirit. Remember, whenever you are allowing for complex numbers, you basically have to make allowances for its real and imaginary part. You cannot just equate this with just two terms, right? So therefore, there will be 4 equations, and that's understandable. Now, I leave it to you as an exercise to show that a plus j a bar, the complex conjugate of this is equal to b plus j b bar. Yeah, this has nothing to do with this 5s plus 2, by the way. You can take this as ps plus q, and you should still be able to show this. Okay, just to show you how this is done, a step. So this is, although this is an exercise, but you can, again, to prove this, you have to just equate coefficients. So cross multiply both sides by this denominator. So you will then be left with a plus j a bar times s plus a minus jb plus b plus j b bar into s plus a minus jb is equal to ps plus q. Right? In this case, of course, p and q are 5 and 2 respectively, but you can choose this to be anything. So you basically you can equate suitable coefficients. So these p and q are, by the way, real numbers, right? So p and q are real numbers. In this case, they are 5 and 2, but they could be any general real number. So obviously, if you're equating both sides, you have to equate not just the coefficients, but you have to equate the real and imaginary parts of the coefficients. So clearly, the right hand side has no imaginary coefficients, right? Because these are real numbers. So the imaginary parts of the coefficients are 0. So if you just equate those two imaginary parts of the coefficients, you'll find that eventually you land up with a bar is equal to minus b bar and a is equal to b. Okay, that is the part of the exercise. So this is the exercise that you have to show. Okay, I've already solved it almost entirely. The point is that once you have complex poles, you can treat with them, you can deal with them in exactly the same fashion as you've dealt with real numbers. In addition, you can use this information that these will be complex conjugates of one another. Okay, so you can always take this same method here. The benefit is that you now have an analogous method, but the disadvantage is that the moment you come up with these, you will see that the terms will be something like z1 e to the power p1t plus z2 e to the power p2t, for example, right? z1, z2, p1, p2 are all complex numbers. So you have to now take again the real parts and the imaginary parts and put them together. All right, and then you will see that this eventually yields terms such as e to the power alpha t cos beta t and e to the power alpha t sine beta t when you take the Laplace inverse. Why so? Because you see, if you have this z over s minus p1, it is nothing but z1 times e to the power p1t, the Laplace inverse of this. All right, so then you have, and let's say you have Laplace inverse of z1 conjugate over s minus p1 conjugate. Now, if you have a real polynomial with real coefficients, the complex poles will appear in complex conjugates, right? And the coefficients will also be conjugates, as we have seen as part of this particular exercise here, right? So do that exercise and you will be able to see why it follows. Then you will be left with z1 star e to the power p1 star t, right? So then you will have z1 e to the power alpha t e to the power j beta t plus z1 star e to the power alpha t again and e to the power j minus j beta t, because they're complex conjugates, yeah, p1 and p1 star. So then you will have this real part of z1, let's call it a plus jb times e to the power j beta t plus a minus jb times e to the power minus j beta t, this times e to the power alpha t. If you simplify this further, you will see that this is nothing but a twice a e to the power j beta t plus e to the power minus j beta t by 2 plus twice b e to the power j beta t minus e to the power minus j beta t by 2j. Okay, then maybe adjust with a minus sign here. Yeah, something like this, and this entire thing multiplied by e to the power alpha t. Yeah, so you have to go through this step. If you are following this solution along the similar steps as we followed in the earlier case, then you'll have to go through all of these steps. Yeah, sounds a little tedious. So is there an easier method for this? And that is why we'll again harken you back to one of the results that you might have been familiar with. See, if you have omega over s square plus omega squared, you know what this is going to be like, the Laplace inverse of this. This is going to be the Laplace inverse of this function is going to be sine omega t. And similarly, if you have Laplace inverse of s over s square plus omega squared, it will be equal to cos omega t. Now, if you shift this s by alpha, what will happen is, by the same token, if you now shift this, s plus a whole square plus omega squared is equal to nothing but e to the power minus at sine omega t, right? Similarly, you can carry out for this also. It will be e to the power minus at cos omega t. So it turns out that we don't really need first order factors because these second order factors are also fairly standard. So what if, when faced with such complex complex coefficients, yeah, or rather complex poles, right? What if we don't go into this first order mode at all? What if we retain these second order terms, for instance? So let's say you have something like 3 over s into s square plus 2s plus 5, right? What if we retain, of course this will be the real one, what if we retain this as k2s plus k3 upon s square plus 2s plus 5? What if we retain this? What will happen? First term, of course, we can always do this multiplication by s. So we can always take s gs limit s tending to 0 is equal to k1, which in our case will be equal to, what will be equal to, I think it's 3/5 is equal to 3/5, yeah, 3 over 5, that's all that will be. Now coming to the solution of k2 and k3, what are you going to do? Now, because now we are not doing, so this is very typical of only when you have second order factors can you do this. So this is a special trick that we are now going to employ to avoid the tediousness of these computations. All right. So what are we now going to do? Now we are going to multiply by this factor, this entire factor again. So we are going to completely cross multiply like we do when equating coefficients. Remember, here also you can equate coefficients, and that is always a method that's valid for everything. But we are going into all these steps because we are looking for shortcuts, because we are lazy. We don't want to go into those tedious steps. So we are always looking for shortcuts. So here it will be in the following form. We will have this equation. When we want to equate coefficients, we will have this k2 plus 3/5 times s square plus k3 plus 6/5 times s plus 3. We have substituted k1. We have used the knowledge of k1 from this step and applied it here. So that is how it is different from exactly equating the coefficients. While exactly equating the coefficients, all of these would have been unknown. But here, in the first step, you have already employed, wherever you have real poles, apply the standard method, that is multiplying by just that real factor and obtaining the coefficients. Maybe even if they're repeated poles, do that. So obtain all the coefficients, just retain only those factors which you wish to go along with this second order terms, second order factors. So there are only 2 such factors here. So that's how this is going to be. All right. Now if you solve for this by just standard equation of coefficients, you can see that it is easy and straightforward. Yeah, k2 is equal to minus 3/5 and k3 is equal to 6/5, minus 6/5. So that is what the solution is going to be like. Now that we have arrived at all these results, so we know basically how to deal with different types of factors. The one factor that we have not discussed here is, because we have only considered rational functions, so gs has always been of this form, ns over ds, but there could also be some exponentials like these at times. Okay, why? Because if you remember one of the Laplace transform results, there you had this time delay, right? So for example, if you have again this, you can try to prove this as part of an exercise. Sorry, if t minus, I've used tau here, right? F of t minus tau dt e to the power minus st. So if you take the Laplace transform of this delayed fellow, then you will find that, yeah, it's going to be e to the power minus s tau fs That Fs is nothing but Laplace transform of Ft. Yeah. So we know this result. So whenever you have such delays, then you have to be a little careful. Suppose there are different types of delays, right? So if there is 2s e to the power minus 2s plus 3s e to the power minus 5s over s plus 2 into s plus 3 into s plus 4. Yeah. Suppose you have a GS like this. All right. So how do you go about this? Then you have to be very careful as to include these delays. Yeah. So you have to have this e to the power minus 2s, and then you have to have like a over s plus 2 plus b over s plus 3 plus c over s plus 4. Yeah. And you have to have plus e to the power minus 5s b over s plus 2 plus e over s plus 3 plus f over s plus 4. Right? You can see why this has to be done. This has to be done because if you want to see, the fundamental starting point is always you have to equate coefficients. So you have to write it in such a form where you can equate coefficients. So the coefficients, now this numerator is not just a polynomial. Yeah. Equating this to 0 will actually lead to a transcendental equation. Right? So it's not a polynomial. So with every single exponential, you will have expansions of this form. So there will be polynomials weighted by these time delay terms in the time domain, which is like exponentials in the S domain. So now when you multiply this, cross multiply both sides by the denominator, you will find that you will have e to the power minus 2s times a quadratic polynomial plus e to the power minus 5s times another quadratic polynomial. So of course, because it is strictly proper, the numerator can be at most a quadratic polynomial. Of course, I mean, strict properness and all that should not be even considered here because this is not really a rational function. But if you understand it in the spirit of what I'm saying here, right? So that means the polynomials degrees should not be greater than 2, right? So this will allow you to express. So again, you can apply those standard methods that we've learned, and you'll see that it's easy to obtain because when you're equating the coefficients with e to the power minus 2s, then you don't consider these fellows. All right. So I hope that you can actually take this also up as an exercise just to get some practice. And I leave you with one question here. All right. So take so this is the last exercise. So take a transfer function with repeated complex poles and see which method is easier. So I can give you an example. Suppose you have 7s plus 8 upon s square plus let's say 5s plus 20, or rather, yeah, s square plus 5s plus 20. This whole square. Yeah, this is your GS. Remember, we want to get it in some standard form from which we can directly read off the Laplace inverse. Okay, so we want to expand that in the suitable partial fractions form. Okay, so take this example and see which method yields the easiest solution. So are you going to consider this like you do with the real poles like this, and consider some factor like s minus p squared, and s minus p2 squared, and things like that? Are you going to do it that way? Or are you going to try and use this particular method here? Or are you going to simply cross multiply and equate coefficients on either side? Yeah, so what are going to be, first of all, you have to ask the question, what are going to be the factors here? So it is not a trivial question, remember. So again, if you had taken, for instance, 7s plus 8 upon, let's say, s plus 2 whole squared plus s plus 1. Yeah, and if you had just considered this as a over s plus 2 whole squared plus b over s plus 1. I leave it to you to show that this wouldn't have sufficed. You wouldn't have been able to expand this unless you considered this additional term c over s plus 2. Okay, so try to equate this and you will see. Try to pose this as a problem of the form ax is equal to b. Okay, and see what you land up with. You land up with some underdetermined system, right? Or overdetermined system, something like that. So see which is which. Okay, so pose this problem in this particular form as ax is equal to b and see that if you had dropped out this term, why you wouldn't be able to express it in this form. Okay. So by the same token here also, remember the numerator is, the degree of the numerator is immaterial so long as that it is less than the degree of the denominator. It is the degree of the denominator that governs how many such terms will be there and what their form will be. Yeah. So first thing you have to ask is what will be the form of this expansion, the partial fraction expansion. Okay. And the second question is which particular form of the expansion is actually going to help you in obtaining an inverse Laplace transform easily. Okay. Depending on that, you have to see which method is easier. This is a rather longish sort of a problem, but nevertheless, I urge you to try this. So before we close this lecture, the last part that we wanted to discuss here, as you can see now, depending on the location of the pole, you will have these exponential terms, right? So e to the power pi t some zi, right? To be precise, it is these poles, these modes that define what the solution is going to be for your differential equation that you're dealing with. So depending on the pole location, we can categorize the type of responses of the system. So let's say this is a complex plane. Okay, so this is the imaginary part and this is the real part of S. Okay, imaginary and real part. So we could have, say, real poles on the right half plane. This is the RHP and this is the LHP, left half plane. We could have real poles on the left half plane. We could have a pole at the origin. Yeah. So what will this response look like? This will be an exponential decay. What will this response look like? It will also be an exponential decay, but a faster decay. Yeah. Similarly, what will this look like? It will look like an exponential blow up. This will look like a faster blow up because the exponential rate is higher here. All right. What does this look like? It will hold it to a constant value. Yeah. So this is a marginal case. Then again, you can have complex conjugate roots that are also imaginary. So the real part is 0. So these roots, these modes, what will the solution look like? This will be a sinusoid or a cosinusoid, right? So these will appear in pairs. So you cannot look at them in isolation. So similarly, if you have, let's say, complex conjugate roots with real parts, complex conjugate poles with real parts that are positive, then you will have the response that looks something like this. So it is the envelope of this is basically blowing up. Similarly, if you have roots here on the LHP where the real part is negative of the pole, then it will look like a decaying trigonometric function, a decaying sinusoid sort of a response. Yeah. Okay. So these are the behaviors that correspond to these on the left half plane. These are called stable behaviors. Why? Because there is dissipation. Energy is being dissipated. On the other hand, these are where energy is being pumped into the system. So these are unstable. So whenever you have poles on the RHP, yeah, then you call it unstable. The ones on the imaginary axis, you call them marginally stable. But if the imaginary axis poles are repeated, notice what happens when imaginary axis poles are repeated. What happens with repeated poles? You also have a t. Now remember, t into e to the power minus alpha t for alpha greater than 0. Because this exponential is a powerful reducing agent, it decays faster than any polynomial. So you can take t to the power k. So long as the real part of this root or the pole is negative on the left half plane, yeah, this will always decay with time, right? This will always decay. But when you are considering this on the imaginary axis, then this term is no more there. So if you are considering repeated roots or repeated poles, that is poles at the same location that are repeated on the imaginary axis, then it becomes unstable. Okay. So the multiplicity of the poles also matters when you are talking about stability. You can say that when you have only a single pole on the imaginary axis, it's just marginally stable, but the same pole, if you repeat there, then it becomes an unstable system. Yeah, so that is the point I wanted to discuss. So with that, we come to the end of this module, and see you on the other side of the break in the next module. Okay, so thank you very much. I'll stop recording.